The basic function of an operational amplifier is to take a small signal and make it bigger. Let's see how this is done. A signal is first applied to a pair of inputs, called the inverting input and the non-inverting input. The voltage applied to the op-amp, simply called the input voltage, is found by taking the difference between the voltage at these two inputs. Here are two simple examples. Notice that the input voltage will be positive when the voltage on the non-inverting input is greater, and negative when the voltage on the inverting input is greater. The signal is next amplified using the op-amp's power supply, consisting of a positive and negative voltage rail. To determine the output voltage of an op-amp, we need to know the amount by which the op-amp amplifies the signal. This is known as the open loop gain. Specifically, the open loop gain is equal to the ratio of the output voltage to the input voltage. Rearranging the equation, we can express the output voltage as a function of the input voltage. If we look back at the waveforms from the start, we see that every point has been doubled, meaning that in this case, the gain would be equal to 2. One surprising feature of op-amps is that their gain is usually in the hundreds of thousands. This doesn't result in an extremely high output voltage, as the output voltage is limited to the voltage range of its power supply. Instead, this extremely high gain will cause the op-amp to become saturated at one of the two voltage rails, distorting the output. We'll see how to decrease the gain of an op-amp when we discuss negative feedback in a subsequent video. As the power supply will typically be the limiting factor, we usually don't need to know the amount of gain an op-amp can provide. For this reason, we tend to consider the ideal case and assume that op-amps have infinite gain. This is just one of several important assumptions that we'll make while analyzing op-amp circuits. Another property of the ideal op-amp is that the inputs have infinitely high impedance. This means that ideally no current will flow in or out of the inputs. Additionally, an ideal op-amp has zero output impedance. Thus, ideally, there shouldn't be a voltage drop when a current passes through the output. We'll add more to this list later on. Before we can make our first practical circuit, we must choose which op-amp to use. Arguably, the most well-known op-amp is the 741. Although it was developed in 1968, it's still commonly used in education. The UA741 includes two offset pins to compensate for slight manufacturing asymmetries, which we'll leave unconnected. There's also one pin that is not connected to the op-amp. Note that datasheets will often label pins slightly differently. To provide the positive and negative rails, we can use two 9-volt batteries connected in series. This provides a total of 18 volts, but if we consider the connection between the two batteries to be at 0 volts, or ground, then the power supply's voltage will swing between positive and negative 9 volts. Careful not to connect these backwards, as this will destroy the IC chip. To test the op-amp, we'll place 1 volt on the non-inverting input and tie the inverting input to ground. To produce 1 volt, we can use a voltage divider between the positive 9 volt rail and ground. As the output should be constant, we can measure the voltage using a voltmeter connected between the output and ground, though you can also use an oscilloscope. As the voltage is greater at the non-inverting input, we should expect the output to be equal to the positive voltage rail. Here the yellow trace is measuring the positive voltage rail, and the blue trace is measuring the output from the op-amp. We see that the output is actually about half a volt less than the op-amp's positive voltage rail. This is normal, as most op-amps can't output voltages all the way to their positive and negative rails. Some will be able to reach one of the rails, and some, known as rail-to-rail op-amps, can reach both. If we look at the datasheet for the UA741, we see that when using a power supply of plus minus 15 volts, the output typically varies between plus minus 14 volts. So we should assume that we'll lose about 1 volt from each rail. Another popular op-amp is the LM358, which contains two op-amps in the same size package as the UA741. This chip is equivalent to 1/2 of the LM324, which contains 4 op-amps. Note that both of these chips label the negative voltage rail as ground. This is largely a difference in naming, as ground is a matter of reference. If we again use two batteries for the op-amp's power supply, we see that if we consider the battery's negative terminal as ground, then the positive voltage rail will be at 18 volts. So we can use these chips just as we use the 741. The reason that the LM358 and LM324 label one voltage rail as ground is that these op-amps are capable of outputting all the way to their ground rails. This makes these chips particularly useful in circuits where negative voltage rails are not available. Let's compare the maximum and minimum output of the LM324 and UA741 by using the same setup as before, but instead of placing 1 volt on the non-inverting input, we'll apply a sine wave from a signal generator. This results in 2 square waves, the blue trace being the UA741 and the yellow trace being the LM324. If we compare the maximum and minimum outputs of the two op-amps, we see that the UA741 is able to output a slightly higher output, but can't get nearly as close to the negative rail as the LM324. We'll see some more shortcomings of the LM324 in future videos, but for now it will be our go-to op-amp.